Hello students, so good evening. So please tell me, can you all see the screen clearly and can you hear me? So please do respond. Please type in the chat box. So can you all see the screen clearly and can you all hear me? Yes? Yes? So please do respond. Can you all hear me? Yes. Okay. Yeah, good evening. So fine. So let us quickly recollect yesterday's things and the past two lectures that we have discussed. In fluid mechanics, we have started our first chapter, fluids and its properties, and we have seen what is a fluid in detail, correct? So we have seen the basic discrimination of a solid and a fluid, correct? So once we have seen that, we have seen, so in solids basically we write that the stress or the shear stress is generally proportional to the strain, but of course this is the case of solids. This is the case of solids, and now in fluids, we write that the shear stress is directly proportional to the rate of shear strain, correct? So this is proportional to the rate of shear strain. This is what we have seen in fluids, correct? This is what we have seen in fluids, correct? And of course, coming to one very important thing, we have seen Newton's law of viscosity, and in Newton's law of viscosity, we have seen that this shear stress is proportional to d phi by dt, and of course, in a very special case that if your body is having, if your fluid is moving at a layer velocity u, and if a layer which is at a distance dy from this is moving at a distance u plus du, and if the variation means this du by dy is constant throughout, then this case we deal this Newton's law of viscosity as tau is directly proportional to du by dy. We have seen all these things, correct? So we have seen all these things. So we have identified what is this Newton's law of viscosity. So then after we moved on to what is this proportionality constant, basically this dynamic viscosity, and in dynamic viscosity we have also seen the SI units of dynamic viscosity, MKS units and CGS units, and we have also seen the conversion of SI units of dynamic viscosity to CGS units, correct? So we have seen that 1 poise is equal to 10 to the power minus 1 Newton second per meter square, correct? This is what we have seen. Correct? This is what we have seen basically. So in CGS units, in CGS, poise is the CGS unit of dynamic viscosity, and of course this poise is equal to 10 to the power minus 1 Newton second per meter square. This is what we have seen, and of course then we have seen how this mu varies with temperature, correct? So as temperature increases, dynamic viscosity of liquids increase or decrease. You please respond. Please do type in the chat box. As your temperature increases, the dynamic viscosity of the liquid, quickly recollect from yesterday's class. So please tell me, as your temperature of the liquid increases, your dynamic viscosity of the fluid, it increases or decreases? We have seen in yesterday's class in effect of viscosity on effect of temperature on viscosity. So please do respond. It decreases, correct? We have seen because there is some reduction in the cohesion of the molecules, and of course we have seen clearly that this mu is proportional to the it's roughly exponential, so a into e power minus bt. This is the law that we have seen. Yes, decreases. All of you are correct. So differences between dynamic and kinematic viscosity also we have seen in yesterday's class. So for gases, if you take for gases, this mu is directly proportional to square root of t. This is what we have seen, correct? And of course we have, yes, it increases, of course. So in gases, as your temperature increases, the molecular momentum transfer increases and your dynamic viscosity also increases, correct? This is what we have seen clearly in yesterday's class, and then yes, it increases, correct? So also we have seen that how this dynamic viscosity is varying, and finally we have seen what is the definition of this kinematic viscosity. This is mu by rho, correct? And we have seen why this combination of mu and rho is very important for us, because this mu itself is nothing but the property that talks about imparting momentum disturbance into the fluid, correct? Momentum disturbance. This property mu is responsible for imparting momentum disturbance into the fluid, whereas this density rho is nothing but it is the property because of whose inertia is more. This property sustains, it tries to sustain the momentum which the fluid is having initially. So basically this is the ratio of two contradicting properties. One property, the viscosity, is because it's trying to stop the, it's trying to change some momentum of the fluid, whereas this density, because of the inertia it's having, definitely it tries to move. So T is absolute T. Yes, T is absolute, correct? T absolute is nothing but absolute temperature, and generally this T in absolute is nothing but in Kelvin, and this is equal to T in degree Celsius plus 273.15. This is what we have, and this something is given in temperature, we take the units in absolute temperature, and of course we substitute here in both the cases, correct? This is what we have seen. So can you all recollect till this point? Can you all recollect till this point? So please let me know. Can you all recollect till this point? Yes or no? Can you all recollect till this point from yesterday's lecture? We have seen what is kinematic viscosity, what is dynamic viscosity, what are different effects of temperature on this dynamic viscosities and all. And also we have seen that the kinematic viscosity of water is less than kinematic viscosity of air because of density variations in both the things, correct? Yes. So see here. Now, if we are clear till this point, then let us come to today's class. Like basically today's class is about discussing a bit of Newton's law of viscosity and also regarding classification of fluids, correct? So let us try to write them. So Newton's law of viscosity, you have seen that tau is directly proportional to the rate of shear strain rate, but of course in a case of linear velocity profile, this tau is equal to mu into du by dy, correct? And this is of course a linear velocity profile case. Linear velocity profile case. And now you see many fluids in which this equation is obeyed by these fluids. For example, if you take water or oil, mercury, all these fluids, they generally obey this Newton's law of viscosity. Okay, and these fluids which obey this Newton's law of viscosity are called, do you have any idea what are the fluids named which obey this Newton's law of viscosity? What are the fluids that are named after the, yeah, it will cover a bit of ESE syllabus as well. So Sajal Sharma, no issues, but please respond, what are the fluids named that obey this Newton's law of viscosity? They are called nothing but Newtonian fluids, correct? So Newtonian fluids are the fluids, yes, Newtonian fluids, very good, correct? Manu, Rahul, Yesu, Tanigai, Velan, okay, Agal, correct. So Newtonian fluids. So we'll see a clear description how this Newton's law of viscosity is generated, or how a special case of some other equation is this Newton's law of viscosity. Okay, so for knowing that, we need to have some knowledge on this, which is, let us decrease this a bit. Okay, fine. So let us look into this Ostwald D Wallace model. There is something called this Ostwald D Wallace model. So what is this Ostwald D Wallace model, which is some advanced work? Thank you, Sajal. So see here. So this is Ostwald D Wallace model, and let us see what is this Ostwald D Wallace model. Okay. So first of all, look, you know, definitely this shear stress acting on any layer of fluid, of course, in case of linear velocity profiles, this is proportional to the velocity gradient of the fluid, correct? Of course, this in case of linear velocity profile only, we are telling you. And generally your dy will be very small, such that you make this approximation for any fluid in general for analysis purpose. Okay. So now one thing that this Ostwald D Wallace gave is this tau is equal to m into du by dy whole power n. This is what he gave us, du by dy whole power n, where this n is called flow behavior index. Flow behavior index means basically this n, or this exponent, is the thing that defines us how a fluid behaves. When you are trying to impart some shear strain rate, then how this fluid behaves is given by this particular n value. And also this m is nothing but flow consistency index. Flow consistency index. Okay. So these are the two constants m and n that give us the idea on how a fluid behaves when these fluids are subjected to du by dy. Now, coming to the case of Newtonian fluids, your dynamic viscosity stays constant, correct? It's well known fact for us, because if you are having some linear velocity profile, then tau is equal to mu into du by dy, and of course these two are, if you are trying to plot this, then this mu remains constant. And we have seen in case of Newtonian fluids, if you take this tau on one axis and if you take this du by dy on other axis, then definitely you are having a straight line passing through origin, correct? But this need not be the case with all the other fluids, correct? I am telling you, this need not be the case with all the other fluids. Why? I will tell you. Look, if you take this law, which is the generalized sense of that Newton's law of viscosity, now depending on these values of n and m, the flow or the fluid nature changes, correct? How it changes? Let us look. See carefully. Let us suppose this tau is equal to m times du by dy whole power n. This is what we have, correct? Now see carefully. This implies tau is equal to m into, can we write this term as du by dy into means the velocity gradient into, your screen is little blur, not visible properly. Is that the case? to all of you. I think you can change the resolution. That will help you out. And all of you, if you liking the content of this channel, please like the video so that it will increase the reach of the content. And since we are offering this for free, this goes to many others who are in need of this. Okay, so please do like the videos. And if you are on this channel for the first time, please do the subscription as well so that you will get notified from the lecture first itself. Okay, fine. So this can be written as m into du by dy into du by dy whole power n minus 1. Du by dy whole power n minus 1. Correct? Can we write this? Now, one very important thing is if you write this tau divided by du by dy, tau divided by du by dy here, in this case, this is equal to m into du by dy whole power n minus 1. Correct? This is what we have. Du by dy whole power n minus 1. Now, see carefully. See carefully. If this is the law that you have, normally in Newton's law of viscosity, you have seen one thing. This tau is equal to mu into du by dy, which means if you make a little manipulation here, this tau divided by du by dy, this tau divided by du by dy is nothing but dynamic viscosity. And this is constant, correct, in case of Newtonian fluids. But I told you all the fluids need not behave similar to Newtonian fluids. So in that case, what we have, look carefully here. If this is the case, then tau by du by dy is called mu apparent. You know, apparent is something that which is not constant, correct? So this mu apparent value changes if this du by dy is changing. Whereas in case of Newtonian fluids, your dynamic viscosity is a constant, but there are few fluids which behave like non-Newtonian fluids and whose dynamic viscosity is changing with respect to this velocity gradient. If this velocity gradient is changing, basically if the shear rate is changing, then definitely this mu apparent value changes, because you can see clearly here this mu apparent is a function of du by dy, which is basically the shear strain rate of any general fluid. So if that's the case, if shear strain rate is changing, then this value is changing. Now, one very important thing, how to plot these fluids. Look, you know, fluid is something which deforms continuously under the action of infinitesimally small shear stress, correct? Now see carefully. If you try to plot this, look, let me plot here, okay? Let me plot. So see carefully. This is what you have here. Fine. So normally if this is your origin, and if this axis, if you are using for replacing this velocity gradient du by dy, and if this is for your tau, now see carefully. If you want to plot a Newtonian fluid on this, definitely you know this tau and du by dy are exactly proportional to each other. And if you want to plot a Newtonian fluid on this, definitely you will plot, let me use a line so that for neat sketches. So see carefully here. Yes, okay, I maintained something passing to origin. Okay, so this is your Newtonian fluid and it's very well known to us. We have been plotting this since past 2 lectures. So Newtonian fluid. Now one very important thing. Let us suppose if your shear strain rate is increasing, means du by dy is nothing but in general case of fluids, this is nothing but d phi by dt, correct? If your shear strain rate is changing and if your n value is less than 1, look carefully, I am asking you, let us suppose if your n value is less than 1, if your n value is less than 1, then as this du by dy increases, this total term will increase or decrease. If your n value is less than 1, means if this exponent is negative, then if this exponent is negative, if your du by dy is increasing, means basically if your shear strain rate is increasing, then what happens to this total value? It increases or decreases? Please respond. I am telling you, whenever this n is less than 1, if you are increasing this du by dy value, then this total value which is here will increase or decrease? It will decrease, correct? It's obvious, it decreases because the top power is less than 1, correct? Suppose if you are having 2 power 0.5 and 4 power 0.5, out of this which is more? Definitely this will be more, correct? I'm sorry, if you put minus 0.5, then definitely you can see that this will be 2 power minus 0.5 will be more, correct? Look, I am repeating, because if your n minus 1 is negative, if n is less than 1, then this n minus 1 is negative. So you can see clearly whenever you have negative signs, this 2 power minus 0.5 will be definitely greater than this 4 power minus 0.5, correct? So because of this negative power. So which means, can you understand one thing? As your du by dy is increasing, this slope tau by du by dy is decreasing. Yes or no? Please try to understand. As your n is greater than, n is less than 1, this value keep on decreasing as you keep on increasing this du by dy, correct? So as you keep on increasing this du by dy, this value decreases, which means the slope of this fluid on this tau versus du by dy diagram decreases. Will you all agree with this? if the slope is decreasing with increase in shear strain rate, how would the graph look like? The graph would look like something like this. So you can see clearly here, correct? And what is the physical meaning of this graph? Let us see. If you try to construct a tangent here, if you try to construct a tangent at this point, let me try to construct. So if you try to construct a tangent at this point, the tangent is a bit steeper, correct? But if you try to construct a tangent at this point, then it is steeper, but of course it is less steeper as compared to this, correct? So similarly, if you try to construct a tangent here and finally here, so one thing that you can observe in common in all these things is, as your du by dy is increasing on the x-axis, the slope of the tangent is decreasing, correct? This is what you can clearly see. The slope of the tangent is decreasing. That means with the increase in shear strain rate, definitely with the increase in shear strain rate, your apparent viscosity is decreasing. And this is the case when generally n is less than 1, because when n is less than 1, this value keep on decreasing as you keep on increasing this du by dy. This is one thing that is very clear. Now, if you reconsider the things, if n is greater than 1, then when n is greater than 1, as you keep on increasing this du by dy, this complete term keep on increasing, correct? So if this complete term keep on increasing, then definitely you can get your graph something like this, look, which we'll be plotting now. Let us use some other color. Okay, so see now. So you can see clearly the graph looks something like this, and of course this is the case when n is greater than 1, and this Newtonian is the case when n is equal to 1, of course, correct? So n greater than 1, and these fluids which are having n less than 1 are called, you know this, these fluids are called pseudoplastic fluids. And of course, if these fluids which are like this, which are increasing its apparent viscosity with respect to increase in this velocity or this shear strain rate, then these fluids are called dilatant fluids. And what is the meaning of these dilatant fluids? See here, what is the meaning of these dilatant fluids? Normally, if you try to draw, the tangent to this, initially your tangents, initially your tangents are having a bit of less slope, but as you keep on increasing the velocity strain rate, your tangent slopes is increasing, correct? You can clearly see the tangent slope is increasing in this case. Means that your orientation of the tangent is increasing, which means it indirectly tells us that the slope value tau by du by dy value keep on increasing, correct? How is n less than 1 and how n greater than 1 is plotted? Look, because when n is less than 1, as your du by dy increases, this complete value keep on decreasing, which is nothing but the slope should keep on decreasing. So you need to draw a curve which has the high slope initially, but as it passes on, its slope should decrease, means the curve should get flattened. Okay, so that's how we have plotted these two curves on this diagram. Are you all clear till this point? So please do respond. Are you all clear till this point? That are you all understanding why this n less than 1 is the curve of this format and n greater than 1 is the curve of this format? Initially they are increasing steep, but of course they are getting flattened in this case, but in this case it's taking a steep curve. Are you all clear? Yes. So did you all understand how the graphs of this pseudoplastic fluids and dilatant fluids are plotted on tau versus du by dy diagram in your textbooks? Yes or no? So please do respond. Please do type in the chat box. Are you all clear how these plots are done? Clear? Good. So now let us write some examples of these fluids, because few times in exams, they ask you for the examples as well. So see carefully. So in case of Newtonian fluids, you can take the examples of air, which the dynamic viscosity of air is very less, and of course water, which you generally treat as Newtonian fluid, and some oils that you deal with in general, all the oils that we are dealing with, and of course we have some kerosene as well in this list. So kerosene, and you can also add mercury in this list, and these are the fluids that we generally encounter, etc. Okay, so these are the general fluids that we treat as Newtonian fluids because of the less variations in viscosities with respect to shear weight strain. Okay, so now if you consider dilatant fluids, now what are dilatant fluids? So dilatant fluids are the fluids basically in which your apparent viscosity keep on increasing as you increase the shear strain rate, correct? So these fluids, dilatant fluids, they are also called by the name, shear thickening fluids. You can write this shear thickening fluids. Why they are called shear thickening? Because as you keep on increasing the shear strain rate, the apparent viscosity keep on increasing, which means the fluid is getting more thickened. Okay, so that's why this name shear thickening fluids is given, because if you are trying to increase the velocity gradient, or if you are trying to increase the shear stress strain rate, then definitely your apparent viscosity is keep on increasing. If your apparent viscosity is keep on increasing, that means the fluid is getting more thicker. Okay, so that's why they are also named as shear thickening fluids. Okay, and if you try to point out some shear thickening fluids, you can take butter as an example, and of course rice starch. Basically your starch solutions in your rice, they make this list. And of course there is sugar suspension of sand with water. You can take this suspension of sand with water in general. Suspension of sand with water. And some other organic solution like a saturated sugar solution. Saturated sugar solution. You can take this into list. Okay, so etc. These fluids could be more than enough. So these are the fluids in general which they keep on increasing if you try to increase the shear strain rate. Okay, similarly glue and all, of course. So now I just want to give you the idea, so I am writing only few names here. If you take the idea of pseudoplastic fluids, and these fluids, they are also called shear thinning fluids, because you see, as we keep on increasing the shear strain rate, then your n value is less than 1 and your apparent viscosity is keeping on decreasing, correct? So as you are increasing the shear strain rate, your apparent viscosity keep on decreasing. So you can say that they are shear thinning, means the more you increase the shear strain rate on them, the less is the apparent viscosity. So they are also called by the name shear thinning fluids. Shear thinning fluids. Okay, shear thinning fluids. And if you take the examples of this shear thinning fluids, so basically if you take the examples of this shear thinning fluids, no, ink is not this Sumit Ajaya. So see here you can take this blood, which is the blood. Of course, if you blood is experimentally proven to be a pseudoplastic fluid, so we take this into the list. And of course milk and some polymeric solutions. Generally, polymeric solutions are organic solutions, so they come under this category. So polymeric solutions generally. And of course you can also write your, after polymeric solutions, you can write your rubber. Rubber is also in liquid state, it behaves as a pseudoplastic fluid. And of course one last example that you can always write here is latex paint. Latex paint. Okay, so these are the fluids which generally they behave as pseudoplastic fluids. Okay, when you are trying to, yes, latex paints, correct? Now if this is the case, so see clearly here, if this is the case, now we have studied the definition of fluid as the substance which deforms continuously under the action of infinitesimally small shear stress. But in actual cases, there are few fluids which are named as viscoelastic fluids, and these viscoelastic fluids, they need certain initial yield stress to start their deformation. For example, let us talk a bit about viscoelastic fluids. Viscoelastic fluids. Now in viscoelastic fluids, normally what happens, how can we feel the liquid is more viscous and less viscous? Just you try to put your hand and try to move your hand. Okay, if you feel more resistance for your hand movement, that means the fluid is more viscous, and if you can easily move your hand, that means the fluid is less viscous. Okay, it's just some manual inspection that can be done. So see here, in viscoelastic fluids, normally these are the fluids, they need certain initial yield stress to start their deformation. As soon as you start, if you apply this infinitesimally small shear stress, they don't start deforming. For example, you might be daily brushing your teeth at the morning and you can use your toothpaste. Is your toothpaste coming out of the tube as soon as you start pressing it? Means, if you apply infinitesimally small pressure, like if you are just touching your toothpaste like this, then is your toothpaste coming out of your tube? Is that happening to any one of you? Is it happening to any one of you? No, correct? Because you need certain yield stress to start the movement of the semi-solid, definitely. So those fluids which are in such situation, they are called viscoelastic fluids. And in viscoelastic fluids, there are again categories. Okay, so there are again categories. What are they? First of all, let us talk about ideal Bingham fluids. Ideal Bingham fluids. So what are these ideal Bingham fluids? Look, they need certain yield stress. Means if you see the equation, this tau is equal to tau y plus mu into du by dy whole power n, of course, and generally this value of n is equal to 1 in this case. Means initially they don't deform as soon as you start applying infinitesimally small shear stress, but if you cross this certain yield stress for starting the movement of the fluid, then they behave as Newtonian after taking some yield stress. Okay, so these situations, let us try to plot these situations. So you can try to plot these situations. So if this is the case, then if this is 0, your du by dy and tau, let us suppose this is tau. So in this case, what happens initially, if you take normal fluids, they start their deformation from the infinitesimally small shear stress, means from this particular point. But in case of viscoelastic fluids, they need certain yield stress. So the fluid, rather than starting its deformation at this point, it deforms from some point which is here. Okay, means basically they need some yield stress to start their deformation. Tau y yield. Okay, so they don't start their deformation until and unless you apply certain amount of stress, like your toothpaste, and if you apply your this jam packets, Kisan jam and all, they are semi-solid kind of things, and of course they don't move initially as soon as you just tilt the bottles, correct? So tau y, and once if this is the case, in case of ideal Bingham fluids, if this n is equal to 1, then this is a constant if du by dy is taken in one axis, and if you try to plot this, you will get the curve something similar to this. Okay, so this is the case of ideal Bingham plastic. Let us write that. This is the case of ideal Bingham fluids. Bingham, H-A-M. Okay, fine. Ideal Bingham fluids. Now, if your n is less than 1, as we have discussed in earlier cases, like for example, if n is less than 1, then such fluids are called Thixotropic fluids. Thixotropic fluids. Thixotropic fluids. Okay, so in case of Thixotropic fluids, again your n will be less than 1. Mu into du by dy, of course, and this n value is less than 1. Means basically, along with depending on this, they depend on the time as well because of this yield stress. So now if you see carefully, these fluids, they take some yield stress initially, and you can maybe use this color as well. The fluid doesn't show any deformation till some point, and then it starts deforming, correct? So similarly here, if you see, if you try to plot this Thixotropic fluids, the fluids look something like this, because this n value is less than 1, which means your apparent viscosity should keep on decreasing, correct? So if you try to draw the slope of this, if you try to draw the slope of this, initially the slope is high, but again the slope starts decreasing after some time, depending upon the yes, this looks like a tangent, and of course, and something like this, correct? So your slope keep on decreasing as your time keep on increasing. Similarly, in one last case of fluids, let us talk about Eoptic fluids. Eoptic fluids, and in these fluids, this tau is given by tau yield plus mu times of du by dy whole power n. Again, these all are given by advanced this Oswalds model, and of course this n value is greater than 1 in this case. So we have seen how the plot looks like when n is greater than 1. Normally this plot looks something like this, correct? So it don't fall beyond this actually, so let me draw a proper curve. Fine, so it looks something like this, correct? And this fluid which we are writing here is nothing but Thixotropic, this is Eoptic, yes, Eoptic, and these fluids which we are writing here, they are known as Thixotropic fluids, correct? So these are the three types of fluids which are viscoelastic fluids, where they need certain yield stress to start the rate of shear strain. Okay, so this is what we can see, and of course here you can easily visualize the things that. Okay, so if you are trying to draw a tangent, initially the slope is very less, but as this time increases, you can see. Let us touch this because it's like tangential. So you can see clearly this is something like this. So you can see clearly the slope keep on increasing. Okay, So there are different values of m for this, different fluids. They are taken from the data tables which are very much available. And the study which we study about this all non-Newtonian fluids is called rheology. Okay. So let us sum up these two diagrams on a single chart. Okay. So let us sum up these two diagrams on a single chart. Before summing up, let us do one thing. Let us add the examples of other kinds of fluids as well here, so that you will have a list in a single page. Okay. So let us do that. So once these pseudoplastic fluids are done, then we have started studying about ideal Bingham plastics. Ideal Bingham plastics or ideal Bingham fluids, generally it's called. So in case of this ideal Bingham plastic fluids, so we generally study about this, we have seen our toothpaste, generally toothpaste, and after the toothpaste we have seen jam, and after the jam you can see some dilating mud can also be in this case. Dilating mud and etc. All these cases, basically these fluids, they come under this. Next, if you want to study about, if you want to know the examples of this eopectic fluids, generally these are time dependent, correct? So eopectic fluids. So in eopectic fluids, you can see one very good example always, which is gypsum in water. Yes, grease and all others. Of course, there are many examples. If I keep on writing, it will take some time first. So I'm just giving you some 3-4 main examples in each case that could help you out in some exams as well. Okay. So of course, gypsum in water. So basically, when you suspend some cement in water, then definitely what happens after some time, you feel that it gets dried up, means it gets thickened, and it's the viscosity of the fluid or viscosity of the semi-solid keep on increasing, correct? So this is time dependent, and this is also called as time thickening in general. So time thickening means as time increases, the fluid gets thickened. So time thickening fluids. Next, if this is the case, then let us shorten this a still bit more for adjustments. Okay. So now see here. There is one last kind of fluids which we have already seen, which is the thixotropic fluids. Thixotropic fluids, and these fluids, are generally they are called time thinning fluids. Time thinning fluids because as time increases, the viscosity keep on decreasing in this case. So in that case, this is equal to thixotropic fluids. If you write few examples, you can just write lipstick, which many of the boys might not be having some idea on this because they don't use that generally. So lipstick, and of course along with lipstick you can always write one printer ink. Normally your inkjets that you're having, they are of thixotropic in nature. So this printer ink is also in this case. Rahul, I'll let you know definitely. Okay, no issues. So see here, this printer ink. So this is different classification of fluids, and these are the bit of examples that you can see here. Now let us try to plot all these things, correct? Let us try to plot this diagram and as well as this diagram. Let us try to plot this ideal fluids, and I mean ideal in sense like basically which deform continuously under the application of infinitesimally small shear stress, and this viscoelastic fluids on a same chart. Let us try to do that. Okay, so let us try to do that. So if you try to do this, we can see a big list of fluids here. So yes, so see here, this is your origin. So this is your strain rate, which of course in books we denote it with velocity gradient du by dy, and here this is your tau. Now can you please tell me, if you take any ideal fluid is the fluid which doesn't have any viscosity, correct? Ideal fluid is the fluid, or ideal fluid is the fluid which is inviscid and incompressible in general. Inviscid and incompressible means, what's the meaning of these two terms, inviscid and incompressible? Your viscosity is 0 and your density remains constant, correct? This is the case. So now please respond carefully. If your dynamic viscosity is 0, means on your tau versus du by diagram, let us suppose if you are writing tau is equal to mu into du by dy. Now please tell me, if you keep on increasing your shear strain rate, du by dy keep on increasing, but if your mu is 0 in case of an ideal fluid, will there be any shear stress in between the layers? Will there be any shear stress in between the layers? If you keep on increasing your strain rate, that doesn't matter, but will there be any shear stress as long as your mu is 0? Mathematically also, No. Correct? No, there won't be any shear stress. So which means if you want to plot an ideal fluid in this case, you can definitely plot the ideal fluid starts somewhere here and it goes on something like this. Correct? Because there won't be any shear stress that's acting on the fluid. So you can clearly see the ideal fluid will lie along the axis of this shear strain rate. Correct? So this fluid which we are writing here is ideal fluid. This is ideal fluid. Okay, next one very important thing. If you try to take a perfect solid, okay, in case of perfect solid, will there be any strain rate? Will there be any displacement of molecules? If you apply some external shear stress in layer to layer, will there be any movement of the molecules? No. Correct? Which means, will there be any velocity gradient? It doesn't matter how much stress you apply. If you keep on applying the shear stress, will there be any velocity gradient or shear strain rate of the solid? Will there be any shear strain rate of the solid? No, there won't be any shear strain rate. In that case, if you try to plot ideal solid, the ideal solid goes along this axis. Correct? This is the axis of ideal solid. So you can write this is the axis of ideal solid. Because as how much shear stress you apply, it doesn't matter. There won't be any shear strain rate. So it lies on y-axis. Correct, Sumit? Okay, so this lies on y-axis. Now, if this lies on y-axis, one very important thing. So now if you want to draw Newtonian fluid on this graph, definitely you can plot some Newtonian fluid on this graph as well. So the Newtonian fluid looks something like this. We have seen. Correct? So this is your Newtonian fluid where your tau and du by dy varies linearly, and of course Newtonian fluids, they start immediate deformation as soon as you apply a bit of infinitesimally small shear stress. So this fluid is nothing but you have your n is equal to, let us write this. So you have your, let us shorten the screen a bit. Okay, fine. So now this is your Newtonian fluid, and in case of Newtonian fluid, your yield shear stress is equal to 0 and your n value is equal to 1. Your flow behavior index is equal to 1. This is what we have seen. When tau y is equal to 0, in this equation, if you see this main equation, like for example, tau is equal to tau y plus mu into du by dy whole power n. If you see this equation, then for getting a Newtonian fluid, your n value is 1 and your tau y is 0. Correct? Similarly, if you want to plot a dilatant fluid on this particular axis, if you want to plot this dilatant fluid, now see carefully. We have plotted this initially. So let me use a different color because it's red already. So okay, so let us use this color. So I told you that your dilatant fluid looks something like this. Initially, your viscosity increase will be very small, but of course, as your shear rate keep on increasing, your velocity, your mu apparent viscosity keep on increasing. So these fluids, they are called as dilatant fluids. Dilatant fluids, and your tau y is again 0 for this case, but your n value is greater than 1. Correct? This is what we have seen clearly. When n increases, the mu apparent viscosity increases. Whenever n is greater than 1, if you keep on increasing the shear rate, your mu apparent viscosity increases, which means the slope of the diagram increases. Correct? So we can see clearly initially the slope is a bit low here, but as you keep on increasing the slope, then as you keep on increasing your shear strain rate, your slope is increasing. Correct? That's what you can feel here, which we have also seen previously. So your slope keep on increasing. Fine. Okay. Next, if you want to plot your pseudoplastic fluids on the same plot, we have seen. So if you try to plot your pseudoplastic fluids, we have seen in case of pseudoplastic fluids, as this n value is less than 1, this complete value keep on decreasing. So similarly, if you try to plot this on that particular graph which we are drawing here, so this you will get for your pseudoplastic fluids. Correct? So this fluids is nothing but pseudoplastic, and in case of pseudoplastic fluids, your tau y is again 0, but your n value is less than 1. Correct? This is what we have seen, of course, and you can see clearly with time, as your shear rate increases, then definitely your viscosity, which is initially a bit high, but it starts decreasing. Correct? Its slope starts decreasing. You can see clearly here, the slope starts decreasing generally if you try to observe, and almost here it gets flattened. Okay, that's what you have seen. So your shear strain rate means basically your apparent viscosity keep on decreases as your shear rate increases. Now next, if you go for ideal viscoelastic fluids, in case of viscoelastic fluids, we have seen for starting the deformation of the fluid, you need certain value of yield stress. Correct? So this is your yield stress tau y, which you need to start the motion of your fluid. So in such cases, in case of ideal Bingham plastics, you have seen this variation means generally if the fluid is taken till this point with respect to this, then from here you have a linear variation which is again parallel to something like this. Correct? Let us pull this a bit down and let us try to fix it here, okay, because we'll be having space for other things. So okay, this point settles here, and of course let us read all these two things. So your tau y is still here, okay, so your yield stress is something till here. Now if you try to plot this eopectic fluids on this graph, you will be having your eopectic fluids something, let us try to plot this. It will be a bit closer compared to this fluids, okay. So now this fluids which we are writing here is nothing but ideal Bingham plastics, and of course in this case your tau y is not equal to 0 and your n is equal to 1. And in case of this eopectic fluids which we have seen why this is happening, they are also called time thickening fluids. And so if you try to draw the slopes, initially the slope will be a bit less, but as you keep on increasing the time, the slope will keep on increasing. Correct? This is what we have seen. So the tangents, if you draw at different points, then if you keep on drawing the tangents at different points, then definitely you will be experiencing and increasing the slope. And these fluids which are here are called eopectic fluids. And these eopectic fluids, they are of course time thickening fluids, and tau y is equal to 0 and n is greater than 1. Next, if you try to plot the thixotropic fluids which we have plotted previously here, in this case, in thixotropic case, definitely your fluid starts decreasing its apparent viscosity as your time keep on increasing. Correct? So this is how something it looks, and generally in the initial stages you will be experiencing a bit of high viscosity because of this high slope, and of course as your time increases, this viscosity they keep on decreasing. Okay, fine. So you can clearly see here the slope of the thing keep on decreases, and okay, let us eliminate that and let us try to read out. Fine. This is the case of thixotropic fluids, correct? And in case of thixotropic fluids, if you try to analyze these coordinates, thixotropic fluid, in case of this thixotropic fluids, your tau y is not equal to 0 again, and of course your n value is less than 1. This is the complete classification of fluids, and just you can just adjust this slide accordingly. Correct? So are you all clear how this graph is generated depending upon this shear thickening, shear thinning, and time thickening and time thinning fluids? So this basically, this dilatant fluids are also called shear thickening, because you can see this velocity increases. I mean, as your shear weight increases, this apparent viscosity increases, and finally your pseudoplastic fluids, they are also called as shear thinning fluids, because you can see they are getting, the apparent viscosity is getting weakened as your shear weight increases. Correct? So this is similar is the case here. These are called time thickening because the dynamic viscosity is depending on time here. So time thickening, and of course here in this case they are time thinning. Okay, so this is the case. Clear? So did you get clear idea on how this chart is generated? What are the mathematical considerations behind the development of this chart? Are you all clear till here? Yes or no? So please do respond. Are you all clear till here how this chart is developed? So this line is basically for the ideal fluid, and this is for basically for this ideal solid, and we have some Newtonian fluid that's acting here. I mean that's represented like this, some dilatant fluids and pseudoplastic fluids on this chart, and also time thickening fluids, time thinning fluids, and of course these are the ideal Bingham plastic fluids. Correct? And of course in this case these are the examples, these are the examples of different fluids, but in the notes you will be getting, I'll make sure, okay, now itself I can make sure that this happens. So you can just keep on, if you keep this here, then yes, that's better. So now you can find all the things at one time. This is the graph that's available here. That's a collection of basically all your fluids, and of course this is your examples list. So are you all clear on the classification of fluids? Yes or no? Are you all understanding why we are increasing the slope of this curve, why we are decreasing the slope of this curve and all? Hello Shibang. So clear? Is that clear to all of you? Did you all understand? So how to identify which fluids are shear thinning and which are shear thickening depending upon the Oswalds-Divalis model? Okay, so yes. So do you have any doubts in this? Do you have any doubts till this point? So this is the basic classification of fluids and this is the classification of fluids and this is the different examples of your different class of fluids. Are you all clear till this point? Yes? Very good. Now, let us move on to one very important thing basically. So, we have seen what is this Newton's law of viscosity, correct? Now, let us, Honey, I'll let you know Rahul soon. So, see here. Let us identify some cases of Newton's law of viscosity. I want to just give you some basic applications of this Newton's law of viscosity. So, I'm just writing here. Newton's law of viscosity applications, okay? And you can write maybe in the brackets applications. Now, see carefully. Fine. So, see carefully. If this is the case, look, let us suppose you are having some shaft. Okay. Some shaft is with me and let us suppose this shaft is something like this. Okay. And of course, you have your axis of the shaft as well. So, this is your axis of the shaft. Fine. Now, let us suppose there is some journal in which this shaft is rotating. Okay. So, there is some journal in which this shaft is rotating. Okay. And there is some journal in which this shaft is rotating. Generally. Okay. Fine. So, let us suppose the clearance between the shaft and the journal means basically if you see this is the shaft and this is the journal that you have. If the clearance between them is H. Okay. There is some clearance between them which is H. And of course, if this fluid which is here is filled with some, this gap between the shaft and this journal is filled with some, okay, let me use some different color. Let us use red color maybe to fill the oil. So, this is some oil, okay. This is some oil. Let me fill some oil so that you will get some better idea or understanding on this. So, let us suppose there is some oil that's being sitting here. Generally, if you see the length of the bearing will be very small, but of course, for your understanding, I have just exaggerated this. Okay, similarly here on the downstairs, there is some oil and of course, basically there is some shaft and there is some sleeve, basically some journal, and in between these two, in the annulus, there is some viscous oil which is having some viscosity. Okay, so let us try to plot this viscous oil soon. Okay, because these diagrams look a bit neat when I start explaining, so that's why I'm taking some extra effort, okay, to fill the oil and all. Now, fine, there is enough oil. Color journal means basically there is some shaft and around that shaft there is some bearing kind of thing. Okay, so there is some vacancy so that this shaft can rotate freely within this bearing. Okay, and of course, you know, generally in your applications you will fill this annulus gap between the shaft and the sleeve with a viscous oil, correct? So, this, let us suppose this journal is fixed, means basically the sleeve of the shaft is fixed and fine. This is the case, okay, and this shaft is moving. Now, if this shaft is rotated at some angular velocity omega, let us suppose this shaft is rotated at some angular velocity omega. Now, please tell me one thing, because of the viscous effects here, will there be some power that gets absorbed into this viscous oil to overcome the friction of this, means to overcome the viscosity of this oil? If this shaft is rotating at some power, means if some power is supplied for the transmission, then can you please tell me some power inside which is transmitted by the shaft will get consumed because to overcome this viscous effects of the oil? Yes or no? Correct? You know this? Because if you are rotating the shaft inside a viscous oil, then definitely some power of the some power that is being transmitted by the shaft will get dissipated because of this viscous effects. Now, let us suppose here if you see, if this is the reference about which, if this axis is the reference about which this shaft is rotating, then all the points of this contact of fluid with solid are at equidistant from this fixed line, correct? All these points which are in contact, all these points which are in contact all these points which are in contact with this shaft, I mean all the points that are in contact with this fluid and solid are lying at the same distance from this reference. Yes or no? In that case, if you want to write the equation for power absorbed, means if you want to write the equation for power absorbed, then let us quickly write what is the power absorbed in the bearing. Okay, so let us try to remove this. Okay, so now let us try to move this. Fine. Okay, so if this is the case, we can write power absorbed by the viscous fluid. If you want to get an expression for this, and this shaft is rotating at an angular velocity of omega, and the diameter of this shaft, I could tell you the diameter of the shaft is nothing but capital D. So in this case, what is the power absorbed by this viscous fluid in this shaft transmitting some power? So see here, power is nothing but torque into velocity, torque into angular velocity, which is omega. Correct? We know this. Angular velocity. Power is nothing but torque into angular velocity. So P is equal to T times of omega. Now see carefully. T times of omega. What is torque? Yeah, we'll see. What is torque? P is equal to, torque is nothing but tangential force that's acting into perpendicular distance. Correct? And what is the perpendicular distance between these 2 points? Definitely, if the shaft is rotating about this axis, then if this shaft is rotating, then the perpendicular distance at which there is some velocity on the periphery of the shaft is nothing but radius. So which means you have this torque is equal to force into radius, which is half of this d by 2. And I am writing d by 2 because all these points are at constant distance from this fixed center axis. So let us write this is d by 2 into omega. Correct? This is what we have. So this implies P is equal to, now what is force? Force is nothing but shear stress that's acting into area. Correct? So shear stress tau into area. Now if I say this length of the shaft is L, which is inside this, if I say the length of the shaft is L, which is inside this journal of length L, then can we write force is nothing but shear stress into area of contact of the shaft with respect to oil. So area of the contact of shaft with respect to oil is nothing but pi into d into L, which is the circumferential area or the surface area of the shaft. So pi dl into d by 2 into omega, which is the angular velocity. Now one very important thing. So this P is equal to, see carefully, this shear stress that's acting is nothing but, can we write that shear stress from Newton's laws of viscosity? From Newton's law of viscosity, if we can write this, let us suppose the velocity variation is linear. The velocity variation is linear. So basically this velocity variation which we are writing here, so let me draw it with a different ink so you can identify well. So if you see, the velocity variation is linear in this case. We are assuming because generally this clearances will be very small. So whatever there is the velocity change, we can assume that the velocity change is linear. So if you write that, this tau can be written as mu into, means the dynamic viscosity of this oil into du by dy. So what is this velocity gradient in this case? There is a clearance of h. So, and the velocity that's being changed here is, initially at the edge the velocity is 0, and when it comes to the periphery of the shaft, that velocity v is equal to r times of omega, which is d by 2 times omega in general. So let us write capital D because we are denoting with capital D. D by 2 omega is the velocity into pi dl into d by 2 into omega. This is what we have here. Correct? So if you write the expression for power, finally this power is equal to, power absorbed in this rotating shaft is nothing but mu into, then pi into, now if you calculate omegas, there are 2 omegas, so omega square into, finally if you find this 1, 2 and 3, there are 3 d's, so d cube into, and finally we have one L as well, so L divided by 2, there is 2 2's in the denominator, 4 times of h. This is the formula for power that's being absorbed in this shaft, I mean viscous oil, whenever the shaft is rotating at some angular velocity omega. Is that clear to all of you? when we use surface area and cross section area, it's not like surface area or cross section area, it's basically the area that is in contact with the oil. Okay, so if you see here, if you want to identify what is the area that's in contact with the oil, so pi d is the circumference of the circle, and total pi d into length will give you the total surface area that is in contact with this oil. Of course, we are neglecting this end effects and all, so generally this is the case, and this is the power that you need for transmitting some this is the power that gets absorbed by this viscous oil here. Is that clear to all of you? Is that clear to all of you? Yes or no? So please do respond. Is that clear? Did you all understand how this came? This is just simple mechanical formulas or engineering mechanics formulas that we see in daily life. Okay, so power is torque into angular velocity, then torque can be written as force into perpendicular distance, and force can be written as shear stress into area, and shear stress can be replaced with Newton's law of viscosity. Okay, fine. This velocity gradient, look, velocity gradient is nothing but what is the velocity difference between these 2 points, means for a given dimension in the direction of y, what is the difference in the velocities, correct? So you can see here the velocity is 0 because the shaft is fixed, and if this shaft is rotating at angular velocity of omega, and if this radius is d by 2, then the tangential velocity of these points, all these points will be r by 2, I mean r into omega, which is d by 2 times of omega, correct? So this will be d omega by 2 and into divided by h. Actually, this is du, means this is the variation of this velocity. Here the angular velocity, I mean the linear velocity is r times of omega, which is this d by 2 times of omega, and here this is 0. So d by 2 omega minus 0 divided by h minus 0. That's what we write it for the angular, I mean this velocity gradient. So are you all clear till this point? And if you are liking the content, please do hit the like button so that it increases the reach of the content. Okay, so please like the videos, and also if you are on this channel for the first time, please do subscribe the channel, because we are going to launch many other courses which are helpful for you, and you will be getting notified from the first lecture itself. Clear? Okay. And every day class starts at 9:30 p.m. sharp, so please do attend at 9:30 sharp. Okay, please don't delay the sessions. Okay, so are we all clear till this point? Are we all clear till this point? Now, okay, so if that's clear, let us go for one more application of Newton's laws of viscosity. Okay, so let us see here. Let us suppose there is one plate and there is one more plate as well, and these 2 plates are, let us suppose they are fixed. So let us suppose these 2 plates are fixed. These 2 plates are fixed. Okay. Yeah, coming soon, beta Rahul, no issue. So see here, you people are attending these classes for all these questions, huh? Good. Look here. So if these are 2 plates that are fixed, then see carefully. Let us suppose there is some plate in between. Okay, so there is some plate in between. Now, if this plate is being pulled off with some force, let us suppose this plate is being pulled off with some force F towards the horizontal direction, and let us suppose the distance between these 2 plates is h initially, and let us suppose this distance is HA, and let us suppose this distance is HB. Okay, now in this case, let us suppose the right side or the top of this is filled with an oil of dynamic viscosity mu A. Let us suppose there is some oil that's filling this gap. There is some oil that's filling this gap, and this dynamic viscosity of the oil that is filling this gap is, let us suppose, this is mu A. Okay, so let us suppose the dynamic viscosity of the oil that's filling this gap is mu times of A. Similarly, let us suppose there is some oil that's filling this gap here, and let us suppose the dynamic viscosity of this oil is mu times of B. Let us fill this gap with some dynamic viscosity oil, which is having some dynamic viscosity of mu B. Okay, fine. And let us suppose the area of this plate is A. This plate is having some area A. Means if you take this plate which is perpendicular to this board, then if you look from the top view, this area which you can see from the top view is nothing but A. Now, can you identify what is the force that is required to move this plate? Can we identify what is the force that's required to move this plate? Yes, we can identify. Look, if you want to see, if this is the plate, if you try to draw the free body diagram of the plate, then this plate is acted by some external force F to sustain its motion, correct? And this force F is pulling this plate, and let us suppose this plate is moving at some constant velocity V. So constant velocity V. This plate is moving at some constant velocity V. Okay, so in this case, if this plate is moving at some constant velocity V, then what are the two other forces that are acting on this plate? So if you see carefully, definitely this force F will try to pull this plate to the right, but of course because of the viscous oils that are present on the top and bottom of this plate, these two forces, these two effects, viscous effects, will try to pull this plate in the opposite direction, correct? So if you see, there is some forces that are pulling this in the opposite direction, and of course this force can be designated with tau A, or let us write FA, force on the top side, and this is force on the bottom side. Okay, for FA plus FA and FP. And let us suppose the weight of the plate is neglected, because coming to the viscous forces and all, let us suppose the plate's volume is so much less, so that even if the density is a bit considerable, but because of the very thin plate, if the volume of the plate is very less, then we can neglect the weight of the plate. Okay, so if these are the cases, of course, yes, friction, but in case of fluids, we call this fluid friction as viscosity. Okay, so that's the only thing. So viscous forces, these are two viscous forces. So these are the forces which are acting. Now, if the plate is moving at some constant velocity, look, if there is some external force, means if there is some net force that is acting on the plate, definitely the plate could have accelerated, correct? But if the plate is moving at some constant velocity, that means your plate is under equilibrium. Is that correct? Yes or no? Because you know, by your mechanics, simple mechanics, sigma F bar is equal to mass times acceleration vector, correct? You know this. But here the plate is moving at some constant velocity for simplification, which means this acceleration vector is 0, which means your plate has to be in equilibrium. Sigma F bar is equal to 0 bar, correct? If this is the case, then definitely this is your shear stress that's acting to the left, and of course this is the shear stress that's acting to the left again. So see here, F is equal to FA plus FB. This is what we can write here, correct? Now, what is force? Force can be written as shear stress acting on the top into area of the plate that is exposed to the fluid. And let us suppose that is A. I have told you, if this is the plate which is perpendicular to this board, if you see it from the top view, then definitely you can see the cross section of this plate. Correct? This is what I have told you. So tau A into A plus, what is the friction force that's acting at the bottom? Shear stress in the bottom into, again the bottom area is also A. This is what we know. Correct? So this implies F is equal to, this tau can be written as dynamic viscosity of the oil mu A into velocity gradient. Now let us suppose the velocity gradient is linear. Okay, means basically the velocity is linearly varying, so we can write this here. So if you see this, your velocity keep on increasing, correct? But of course it increases linearly. So let us suppose we are drawing the, okay, let us suppose here the fluid is having some velocity in this direction. Okay, fine. So see here, and you have some velocity, correct? Similarly, if you see in the bottom part, similarly there will be some velocity. You can move this B a bit. Okay, so see here, in this case your velocity again from 0 it will go to some finite value, correct? And of course you can plot the length of the vectors, velocity vectors. Here the velocity is a bit more, and here comparatively less, here comparatively again less, and finally it reaches 0 at this point. So this is how the velocity is getting varied. So in place of this tau is equal to mu into velocity gradient, when these profiles are varying linearly, can we write this velocity is varying linearly, and of course at this point this is equal to the velocity of the plate. So V divided by HA into area plus, similarly tau B is nothing but a mu B into V divided by HB into area. Okay, this is what we have. So if you want to write the total force that's acting on the plate, you can write F is equal to, look, you know this velocity V is constant in both the cases, because if the plate is moving at some velocity V, then the layer on the top which is attached to this fluid, attached to this plate, will also move at velocity V, and in the bottommost part also the fluid layer moves at velocity V, that is in contact with the fluid. So definitely you can see V is common in both the cases, and also you can see the top surface and the bottom surface areas of the plate that are in contact with the fluid is same. So if you take this VA out from both sides, I mean from both the terms, then you have VA into mu A by HA plus mu B divided by HB. This is the total force that you need to move this plate at some uniform velocity V. Okay. Now, one very important thing. Let us discuss some cases in this. So, case 1. If tau A is equal to tau B, means the shear stress acting on both the faces of the plate should be equal. For this to happen, means if you are having a plate and if this plate is moving, then definitely because of the top fluid and the bottom fluid that are present, these two fluids will try to drag this plate. So if these two are dragging this plate, then definitely there are some forces FA and FB. So if these two forces has to be equal, means basically, you know, on both sides areas are same. So that means if I am telling you shear stresses on both top and bottom faces are equal, then that means your top and bottom shear forces that are acting are equal. So this implies FA is equal to FB. Correct? So what is the shear force? Basically we can write tau A into velocity gradient by this velocity divided by HA. So VA by divided by HA into mu A. This is what we can write, and of course this is equal to V by HB into mu B. Correct? Because the shear stresses that are acting are equal, so that means the forces that are acting are equal. So basically if you write the expression for shear stresses in terms of Newton's law of viscosity, this is what you have. So your V gets cancelled on both sides of the equation, and this implies your mu A divided by HA is equal to mu B divided by HB. So this is the condition in which this shear stress acting on both the layers will be same. Okay, so this is the condition. So sometimes they give you this in examination, so they'll ask you out of these 4 values, they'll give you 3 values, and they'll ask you what is the value of the 4th variable, so that this plate experiences same shear stress on both the faces, on top and bottom face as well. So is that clear? Is that clear to all of you? Did you all understand this? Whenever there is some motion of the plate between two fixed plates, and if the plate is moving at some constant velocity, then this is the total force that which you need to apply on this plate, so that this plate moves with some constant velocity V. And also definitely if you are having this tau A is equal to tau B, means if the shear stress on top and bottom has to be same for this plate, then definitely this mu A by HA should be equal to mu B divided by HB. Okay, so is that clear to all of you? So please do type in the chat box, is that clear to all of you? Okay, fine. So is that clear to all of you? So if that's clear, then we'll go for one more case before we end this lecture today. So case 2. Case 2. Location of the plate for F to be minimum. And what is F? The force that you are pulling this plate. Correct? For F to be minimum. Now one thing is very clear. Yeah, forces due to surface tension we need to consider, but here we are not considering the forces due to surface tension, because surface tension generally happens when there is adhesion, and here the movement of the plate and this viscous forces are a bit high as compared to the surface tension forces. Okay, normally your surface tension forces are a bit less comparatively. Okay, those are very weak because they are due to the adhesion between the molecules and some other surfaces, but now we are dealing only with the viscous forces. Okay, we have some separate lecture for surface tension, so no issues. Now if this is the case, so this F is basically depending upon all these terms. Now depending upon these locations of HA and HB, means if this plate is shifted a bit bottom, then this HB decreases and HA increases. Correct? Similarly, if this plate is moved a bit top, then HA decreases and HB increases. So depending upon the values of HA and HB, will your force change depending upon the values of HA and HB? Yes or no? So please respond. Depending upon your values of HA and HB, of course, once your mu A and mu B are fixed, means if your dynamic viscosities of A and B are fixed, so please tell me, will this force gets affected? Yes, it gets affected, definitely. So now let us know how much it gets affected. So if you write, you have F is equal to mu times, okay, V times of A into mu A divided by HA plus mu B divided by HB. Correct? This is what we have. Now, let us suppose, correct, this is what we have. Now, let us suppose this distance h is fixed, correct? The distance h between the plates is fixed. So, HA plus HB is equal to h, and of course, this thickness of the plate is neglected as compared to this HA and HB. So, I am just neglecting the thickness of the plate. So, HA and HB. Okay. So, can we write h is equal to HA plus HB, which means in place of HA here, can we write VA into mu A divided by h minus HB plus mu B divided by HB? Can we write this? Now, if we are writing this, one very important thing that you can observe here, out of all these terms on the right hand side of this equation, this velocity at which this plate is moving is a constant. This area which is exposed to the fluid is also constant for any given plate and fluid situation. Once the fluid is filled, means once these oils are filled, mu A and mu B, this mu A and mu B are fixed. This h, the distance between the plates, is fixed. Now, out of all these terms, which is the variable? Now, out of all these terms on the right hand side, what is the variable? All of you, I need answers from you. So, out of all these values, what are the variables that are involved? Only one variable. What is that? That's nothing but your HB, correct? HB is the only variable, correct? Height, HB, correct? Yes. So, for F to be minimum, what can be done? For F to be minimum, dF divided by dHB. This has to be made 0. Yes, correct. HB is the only thing that is variable. So, dF divided by dHB has to be 0. If this is the case, now if you differentiate this, VA is a constant. So, VA we will write as usual. Similarly, this mu A, now the derivative of 1 by h minus HB is nothing but minus 1 by h minus HB whole square into the inner derivative with respect to HB is minus 1 plus mu B is constant into the derivative of 1 by HB is minus 1 by HB square. This value is equal to 0, correct? And so, one thing you know, these two terms are not 0, and this is minus into minus will give you plus sign. So, let us write that minus into minus will give you plus sign, and this VA is constant absolutely. So, this can't be 0. So, the only one thing that can be 0 from this analysis is your mu A divided by this HB minus h minus HB whole square. This should be equal to mu B divided by HB whole square. So, if you make little manipulations here and there, so mu A divided by mu B, this value is equal to, correct, this is what we have written. So, this mu A divided by h minus HB whole square is equal to mu B divided by HB square. So, mu A divided by mu B can be written as, or maybe square root of this mu A divided by mu B can be written as h minus HB divided by HB. This is what we have. So, similarly, this implies, so if you take, if you split this, then there is minus 1 on the other side. So, h by HB is equal to 1 plus root of mu A divided by mu B, which means your HB can be written as h is equal to, or HB can be written as h divided by 1 plus square root of mu A divided by mu B. Okay, so this is the location of h. This is the location of h. This is the location of the plate at which, yes, aspiration effect in casting. Yeah, it looks similar, but of course, both are pretty much different things. So, I am telling you, this HB is nothing but h divided by 1 plus root of mu A divided by mu B. Look, this point is nothing but, look, we have shifted this mu B to the left hand side. So, if this mu B comes to the top and this h minus HB goes to the top, okay. If there is no square root here, then mu A by mu B is equal to whole square of this, okay. So, this is the location at which this force that is required to pull this plate will be minimum. So, is that clear to all of you? So, anyhow, I think it's time for today. So, let us quickly go through certain basic things that are with us. So, tomorrow we are going to start various cases of Newton's law of viscosity. Of course, we have seen 2 cases today. So, in tomorrow's class, we will see a lot more cases on this Newton's law of viscosity as well. And of course, if you like the lecture, please do like the videos, and increasing the likes will definitely increase the reach of the content so that many others will get benefited out of this. Okay. And finally, we are starting some non-technical sessions as well. So, today, some 6th March at 7 p.m. we are having this session on unlocking unexploring IIT Bombay. So these are two IIT alumni which might be known to you. So VS sir and Negi sir. So definitely these two will be explaining you, like basically revealing you how IIT Bombay looks like, and that eventually provides some more motivation for you to go to that by preparing some exams and all. And of course we are running this, we have started this offline course which you might be knowing already through some messages or through some other portals as well. So in our offline batches, we have started 3 offline batches, and normally if you see, daily we will be having some 5 to 6 hours of the class. Initially we thought of having for 5 hours, so 2 p.m. to 7 p.m. and we are conducting it at our own branch, which is Vishakhapatnam. Okay, and of course in duration we are constraining the schedule to 5 to 6 months. Okay, so in a regular batch you will be finding enough time to learn all your concepts and of course to get acknowledged of all the things. Okay, so we have already started one batch which is running successfully, and we have started this batch on 1st of March, and of course second batch is about to start in 15th of March. But if you want to join, please don't lag the things, try to join immediately so that you will get a chance of revising the things once again at the end. Okay, so and finally one last batch we are going to launch in terms of in the last 29th of March. So definitely these are the 3 batches that we are launching for the regular batch. Okay, next, this is our classroom which you can see, and students are pretty much motivated here, it appears to be. And if you want to sit somewhere in between, you can definitely pull your seat by just contacting our office. Okay, and of course these are multiple ways to contact us, so you can always find some contact you can always find some very good content on Engineers Hub YouTube channel, which you are doing it now. And if you are on this channel for the first time, please do subscribe the videos, and of course please like the content if you are liking it really. And then this is the Telegram channel of Engineers Hub Mechanical, where you will be finding the notes on daily basis, and what are the recent updates about engineering and all other things, they will be posted in the Facebook channel, LinkedIn, and of course you can also find a bit of that in Engineers Hub official website www.engineershub.com. okay, and this is one more Telegram channel for ECE, EEE, civil and all other students excluding the mechanical. Okay, so I hope things are very much clear. So tomorrow, as I was telling you, tomorrow we have a class on this various cases of Newton's law of viscosity. So we will be dealing certain quite good number of examples in which there are a few questions of gate and ESE as well. So please don't miss tomorrow's session. And of course, as I was telling you, I am repeating that there are batches that's being started by us. One batch that's running successfully that we have started on 1st March. Okay, so next batch that we are going to start is from 15th of March. So please don't miss the chance. Next, so I hope all of you are clear with the class today. So let us quickly go through the slides that we have discussed today. So we have quickly recollected what we learned in past 2 lectures, and this is the 3rd lecture. So in 3rd lecture we have seen Oswald-Diwali's general model of fluids, and then we have seen how this fluids look like on a tau versus du by dy graph. And of course we have seen when n is less than 1 why this graph is going like this, because there should be some decrease in the slope, because if this is your mu apparent, then definitely if you keep on increasing this when n is less than 1, then this value, total value, keep on decreasing, so your slope should keep on decreasing. And this is the case when n is increasing, and this is the case of the fluids which start their deformation as soon as you apply some small shear stress. And this is the case of the fluids which are viscoelastic fluids, they need some yield stress for their deformation. And of course these are again 3 different kinds of fluids like ideal Bingham, Eoptic and Thixotropic fluids which you could deal with. Okay, so we have basically summarized all these fluids on a single graph, tau versus du by dy graph, which you can see in many of the standard textbooks, but of course we have seen how these graphs are developed on all the cases. And of course these are the different examples of all these fluids. So these are named as shear thickening, thinning and all, and we have seen why this is happening. Why we have different shear thickening, shear thinning and all the fluids, correct? So we have seen some 2 applications of Newton's law of viscosity, one with the journal, the shaft rotating inside a journal which is bounded by some viscous fluid, and the power that is required to rotate this shaft is nothing but given by this formula. And of course this is the case of moving a plate in between 2 fixed horizontal plates, means basically moving a plate in some horizontal gap. Okay, so this is what we have learned in today's class in a cut short, and of course all these are the details of the upcoming events. And today, yesterday there is a notification out by the Hindustan Petroleum Corporation Limited. So these guys have posted for the job, posted some jobs for mechanical engineers as well. So there are 120 jobs for mechanical, and the equipment is without gate actually. Okay, and the CTC is above 15 lakhs, which is a bit high as compared to the previous situations. And of course in the current situation 15 point something is really a very good package. Okay, so the application has already started from today, and so you can definitely find one of your application there. And of course tomorrow 4th March is the last date for challenging the answers of GATE 2021. So if you feel like you can challenge some questions, definitely make some strong supporting documents and also upload in the official link that is provided in the GATE 2021 website. Okay, so I hope things are very much clear for us. Are you all clear with today's lecture? Yes, so please tell me, are you all clear with today's lecture? Are you all clear? Yes or no? So please do respond. Please type in the chat box. Are you all clear till today's lecture? All the concepts that we discussed? Yes? So please do type in the chat box. Yes? Very good. Fine. Okay. Tanika Velan, Misha, Suyenda, Shubha and all. Fine. Okay, Vienna, no issues. So thank you all for being patient and being here. So can you all tell me what is the timing for tomorrow's lecture? Can you all tell me what is the timing of tomorrow's lecture? Time for tomorrow's lecture on this channel for the 4th lecture of fluid mechanics. Can you all tell me what's the time for tomorrow's lecture on the same channel? 9:30 p.m. Okay. So 9:30 p.m. to 11 p.m. is what every day we are going to have some classes. And of course, if you're liking the content on this channel, please do like the video so that will increase the content age. Okay. Thank you all. Have a nice time. Good night. Wish you a very good luck.